the chain rule. Consider the function z equals f of xy equals x squared minus 2xy squared plus 4y. Let's find the derivative of z with respect to t. So we're going to be using the chain rule from single variable calculus to do this. And we get the derivative of the first part, which is 2x, times the chain out dx dt. Then minus 2y squared times dx dt, because I took the derivative of the x part in the middle of my product rule. And then minus, I'll do it this way so we can see where it comes from, 2x times 2y times dy dt, because now I took the derivative of the y part in the middle of that product rule. And then plus 4 times dy dt. We could have written this as 2x minus 2y squared times dx dt, then plus negative 2x 2y, which I'll put as 4xy, plus 4 times dy dt. And if we took a look at what was going on, we would notice that dz dt equals the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. Just to convince you, at least in part, notice that the partial of my function with respect to x is 2x minus 2y squared. And the partial with respect to y is negative 4xy plus 4. So more generally, and this is not meant to be a proof, this example is not, of course, but just to convince you that this would work for the chain rule. And if we had higher dimensions, for example, if we had w is a function of x, y, and z, then the derivative of w with respect to t would equal the partial w with respect to x times dx dt plus the partial of w with respect to y times dy dt plus the partial of w with respect to z times dz dt. And of course, if we had more variables, we just extend this out. So this is one form of the chain rule in multivariable. Let's take a look at an example. Let z equal x squared y plus 3xy to the fourth, where x is sine of 2t and y equals cosine of t. And we want to find dz dt when t equals 0. So let's write out our dz dt first, just in general form, which will be the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. Then we can substitute the various expressions. So the partial of z with respect to x is going to be 2xy plus 3y to the fourth. And then dx dt is 2 times the cosine of 2t. Plus the partial of z with respect to y is going to be x squared plus 12xy cubed times dy dt, which will be times negative sine of t. And we want to find this, or evaluate, at t equals 0. So let's take a look at what x equals at t equals 0. X at 0 is the sine of 0. Looking at y at 0, so y of 0 is a cosine of 0, is 1. So now we can plug in. Over here we get 2 times 0 times 1 plus 3 times 1 to the 4th, plugging in for x and y, times 2 times the cosine of 0, or 2, plus some other stuff which I'm not going to worry about because I know that the sine of 0 is 0, and so this whole back part is going to be plus 0. So if I were to simplify this all the way down, we would get a value of 6. Let's look at another form of the chain rule. Suppose that z equals f of xy, where x is a function of two variables, say s and t, and y is also a function of those same two variables, s and t. For example, let z equal x squared minus 2y squared, where x is 3s minus cosine t, and y equals a sine of s squared t. And let's find the partial of z with respect to s. Well, that's going to be the partial of, let's substitute in, is going to be x squared, where x squared is 3s minus the cosine of t, and then squared, minus 2 times y squared. So y squared will be the sine of s squared t all squared. So in this case, I substituted in my function x equals a function of s and t into each x and then again for y, so that I could take my derivative, at least the partial, with respect to s. So now let's take the derivative with respect to s, and we get this first part is going to be a power rule first. Bring the 2 down. I'm going to leave this inside part alone, to the first power, times the derivative of the inside part, the partial with respect to s, which would be times 3. And I'm going to put plus, we'll see why in just a bit. So plus, and then negative 2 times 2, so negative 4. So now I'm doing the derivative of this part, or I'm going to bring that 2 down in front, and I'm going to leave this inside part alone, sine of s squared t. But now I need to do the derivative of this inside part, which is also going to have a chain rule. So the cosine, leaving this inner part alone, and then times the derivative of this inner part, the partial with respect to s, giving us 2st. So how can we generalize this? Or what can I see as the pattern here? Well, let me show you here. Notice that I could write this as 2x, where this is x, times the partial of x with respect to s. All right, here's the partial of x with respect to s. And then plus, I have negative 4y. Well, this piece here is y, times the partial of y with respect to s. All of this is the derivative of y with respect to s. But also notice that 2x is the partial of z with respect to x. And negative 4y is the partial of z with respect to y. So in general, when I have z equals a function of x and y, the partial of z with respect to s is given by this. And then the partial of z with respect to t is going to be the partial of z with respect to x times the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. Let's do one example of this, just kind of using our formulas. So let z equal e to the x times sine of y, or x equals s times t squared and y equals s squared times t. And let's find the partial of z with respect to s. Well, that's going to be the partial of z with respect to x times partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. And of course, if we add more variables, we just keep adding plus in a similar fashion. So the partial of z with respect to x is e to the x times sine y. And then the partial of x with respect to s is t squared. Plus the partial of z with respect to y is going to be e to the x times cosine of y times the partial of y with respect to s, this would be 2st. And then the partial of z with respect to t, which is going to be the partial of z with respect to x times the partial of x with respect to t, plus the partial of z with respect to y times the partial of y with respect to t. And now we can plug in. I already know the partial of z with respect to x. It's ex e to the x times sine y. And then the partial of x with respect to t is 2st plus partial of z with respect to y, we already found e to the x times cosine y, times the partial of y with respect to t times s squared.